Bonjour à tous. Hello, everybody. Welcome to our webinar number 5 of this second edition of Copernicus MOOC. So today we have the pleasure to welcome 3 speakers. So our agenda is it's a very interesting one. We'll now have Pietro Seccato, who will talk about satellite images for monitoring natural resources. So it will be 15 minutes presentation followed by a Q&A session. Then at 5:30 we will have we welcome Guillaume Rieux from Tyrannies. We'll talk about resource management, and at 6 o'clock we will conclude with Diana Chavarro-Rincon, who will talk about Copernicus for capacity building. Also same session, so short presentation of 15 minutes and then the Q&A session. So I hope you will enjoy this webinar. I will leave the floor to Pietro. So Pietro, welcome, and you can start the presentation. We will load your document. Yes.
Very good.
Okay.
Excellent. Thank you very much. And welcome to everybody. So I would like to present to you, and I have to see the use of Copernicus satellite images for monitoring natural resources. And for that, I'm going to tell you a little bit about the story of my experience. Now I have some problems in moving the presentation. How can I move? Here it is. Okay. So here, when I started doing remote sensing about 20 years ago, in order to have access to the satellite images, I had to go onto the field and with my antenna, wait for the satellite to pass over. And I was so happy when I was able to access 2 images per day. That was with NOAA AVHRR. And as soon as I had 2 images on my computer, the computer was full and I had to back up the images. And since then, we have had now access to many other satellites, and especially the Copernicus satellites like Sentinel-1 on the left, which is the radar system, and Sentinel-2 on the right, which is an optical sensor and middle infrared there. And so now we have access to massive amount of images that we can access through internet. So now I don't have to go into the field. I can visualize my images via my computer in my office. And those images now we are capable to access them in almost real time. And the technology has advanced so far that with the smartphone, you can even access the satellite images and look at the environment. And on the bottom, I took a pictures of a trip when I was in Tanzania, in Maasai village, where I was doing research on Tripanosomiasis and using the satellite images. And if you look carefully, the third person from the left, the person in blue, is the chief of the village. And during the meeting, he was always on his cell phone and chatting about where to move the cows and knowing what was going on in the villages. So I said, if I am able to provide him the satellite images through his smartphone, he has access to all the possibilities to monitor the environment and make decisions on that base. And so what I did is to be able to, for the chief Maasai, to access satellite images on a massive amount of data in terms of climate and weather monitoring. This is an example of the web page at IRI, Columbia University, that I developed, where the chief Maasai can access the precipitation, the temperature, the vegetation, even forecast in terms of rain, and directly from his cell phone. And now he's using his cell phone to access the satellite images. And what I want to tell you, it's a little bit the stories about the satellite images, how we can monitor important factors that are useful for the user community. And this is an example of all the vector-borne diseases that we can monitor. Obviously, the satellite doesn't monitor directly the dengue fever or the malaria, not even the COVID. But what we can do is to monitor the environmental conditions that affect the vector that transmit the diseases. So, for example, for the dengue and the malaria, that's transmitted by a mosquito. The sleeping sickness is transmitted by a fly. And so we can monitor the environmental conditions that affect the vector and the transmission. And even we can even forecast those environmental conditions with 2-3 months in advance and forecast a diseases outbreak. So I'm going to show you the examples of how I'm monitoring the vegetation and the water bodies for different applications. So in forestry, in agriculture, water bodies about irrigations, about flood events, and the impact on different diseases or managing the environment. So this is an example of a Sentinel-2 image taken in Ethiopia in the Rift Valley, which is all the brown and pink colors here in the middle. So that's a valley that separates now Africa in 2 parts. In a couple of million years, we will have an ocean here. But in this area, which is very dry and very hot, I put in dots, green dots and red dots, the location of villages there. And the green dots shows where we don't have malaria. First of all, because it's too dry in this area. And on the left and on the right part of the images, we don't have malaria because those are highland where it's cold and the mosquito cannot thrive there. But if I zoom in this area, and I hope you can see my arrow, it's just on the northeast of the image. There is a lake there, and with presence of vegetation. And what happened here is that the farmers have started to do irrigations and to grow crops. And if I zoom even higher, here we can see in dark blue here some puddles of water. The spatial resolution of this image from Sentinel-2, it's 10 meters as a spatial resolution. So here what happened is that by creating puddles, that was the source for the mosquitoes to be able to breed. And since they have created irrigation, we have problems of malaria. So in the area where it's very dry, the fact to create irrigations creates the conditions for malaria transmission. And I am able to follow this evolution on almost every week, how the irrigations, how the presence of water is increasing or decreasing. The next slide is about another disease, the Trypanosomiasis. It's the sleeping diseases, which is transmitted by the tsetse fly. Here. And this is a work I did with the Maasai community and with Professor John Hargrove, who in the 70s discovered that the tsetse fly, despite the fact that it has big eyes, it's almost blind. And the fly is attracted by the smell of the cows, by the urine and the acetone. It's the product that exhale the cow. So by eating grass, they exhale acetone. And John Hargrove put those 2 elements, the acetone and urine from the cows, underneath the trap, and the flies is trapped there. So as a suggestion, the acetone is also used as a nail polisher. So if you go to those areas, you would avoid to use a nail polisher in order to not attract the tsetse fly. And so with John Hargrove, what we did is to look at the conditions where we have, and this is a satellite images at high spatial resolution, 50 centimeter, where you can see the house of the Maasai surrounded by a fence there. And the picture that I took where we had the meeting was right there on the left corner and the bottom. And I am able to monitor every week for example, the presence of water. Here it's in the water in October 2016. You can see the blue dot there. There's not much water. And if you look at the bottom left of the screen, you have 3 points. That's the point where we had the trap there. And the traps are located in the forest line here, because the fly will stay there to protect itself and then fly to the lake when the cows are drinking. They bite the cows and then they go back there. And by monitoring the water content every month, we can see how the water grows and decreases there. And so there are different risks for the tsetse transmission about the trypanosomiasis. And the good way to control the tsetse fly is to burn the trees here along the river. And we can follow that. In January, it's the rainy season. And I can even follow the vegetation, so the grass. So the chief Maasai can look where and when they have good pasture and conduct the cows towards those regions with a lot of water and grass. So this is an example of managing the diseases. There's another example of managing the fires. And last year, we had in Australia massive fires. Now it's California. And we can, using Sentinel-2 and then also Sentinel-3, monitor the active fires, monitor the smoke and the burnt area. And about 20 years ago, I developed an algorithm to detect the active fires based at that time on AVHRR, but now it's used on MODIS, it's used on Sentinel-3, so that's the same algorithm. So we can monitor that's the fire activities. Another application is pest management, and here the pest is the desert locust, because I worked for the Food and Agriculture Organization, FAO, based in Rome, and the aim there was to monitor the locust, which on the left, it's when it's solitary. When the conditions are dry, it lives in the desert, and that's fine. It doesn't produce any harms. But when we have good conditions in terms of rain, and then you have the presence of vegetation, the locusts gather to eat the vegetation, and by touching each other, they change behavior, they change color, they become yellow, and so they become gregarious. And when they are gregarious, they start forming swarms that will leave the desert and attack the crops in the different regions. Here, this is the Cairo in Egypt in 2004, Mauritania, 1989. Those were the last big outbreaks of desert locusts, except last year and this year in Yemen and then Somalia, and then the swarms start invading the Kenya and Tanzania. So the purpose here is to monitor the presence of vegetation in the middle of the desert and send the control team to check if there are locusts, and if they have locusts, they will do the control. This is an example of the Ministry of Agriculture in Niger, in Africa. They have 2 cars to monitor an area equivalent to the state of Texas or France. So they cannot monitor everything, and they might pass by a patch of grass where there are desert locusts, but at 2 kilometers. So what they do, they use the satellite images that I provide using Sentinel-2, and they can monitor all Niger and zoom in places where they have presence of vegetation. So this is in the middle of the desert, and if I zoom even more, you can see in green the presence of vegetation, and this is the picture they took when they went to the site, and they found locusts, and they were able to control. So this is a great system to monitor and send the control team in the places where we have vegetation in the middle of the desert. What happened with the last outbreak in Yemen and Somalia is that we were able to monitor the vegetation using the satellite images, but we couldn't send any control team because in Yemen there's a war and Somalia is dangerous too. So we couldn't monitor the presence of desert locusts there, and we were caught when the swarm left Yemen and Somalia and reached Tanzania and Kenya. And when you have the swarms there, it's almost impossible to fight them. It's too late, there are too many of them, and so they reproduce, and the whole purpose there is to try to control the locust as best as we can. But we had the technology to monitor the presence of the vegetation and even the rainfall before, but we couldn't send any locust control team there. Next one is the natural disaster, the flood, and for index insurance. So here I'm using Sentinel-1 on the left, which is the radar system that I can monitor the floods. Fortunately, there is an animation there, but it doesn't look like it's working. But you could see how the flood impact the villages. And on the right, I'm also using Landsat 8 or Sentinel-2 to monitor floods, in this case in Bangladesh. And we have a paper explaining the methods that we have developed, which was published in 2018. The next one is the impact. What is the impact of floods on the population, on the infrastructure? And here we have to be careful about the source of data that we use. In terms of population, we have three sources of data. The global footprint from DLR, the world population, and the Joint Research Center dataset. And depending on the dataset, we have different responses, the different results. So it's always good to check the sources of your data before doing an impact assessment, looking at the quality of the data. Next one is now how can I access the satellite images? So 20 years ago, I had to go on the field with my antenna, but now I can go to the website of Copernicus, of the European Space Agency, but it takes time to download the images, and sometimes the format is not always easy. You have HDF, NetCDF, other format. So if you're not an expert in remote sensing, it's very complicated to access the images and to process them. But now, with Google Earth Engine, you can access those images because they are able to fetch and collect all those different data sources, and you can visualize them in a very quick manner, all the different images that are available on the market. And so this is, in order to access the Google Earth Engine, first you have to sign into the website there, with your Gmail account, and then so you can do that later. And once you have access to that, the beauty of the Google Earth Engine is that they are able to split the images in tiny tiles and send the processing in different servers. And that speed up the process. Now to look at 30 years of Landsat images, you can visualize them in 5 seconds, and you can process them. So there's a massive change in the way we handle the images. So thanks to Google Earth Engine, you are able to access and manipulate the data, visualize them, do some algorithm, and extract some interesting information. So this is the link for Google Engine. I'm just going to show you quickly how to navigate in it and how to access Sentinel-2 images. So on the bottom left, you have the classic tools to move and to draw layers of boundaries, of points. And on the right, you can look at the map or the satellite images at high spatial resolution. On the middle, you can code and write your script. It's in JavaScript. On the left, you can save your project. And on the top, you can get the URL link that you can share with other specialists there. Use the save button, run the program, and you are ready to start to work with the data. In order to access the data, there is an import box there, and here I'm choosing Sentinel-2. That you scroll the list of images that you have, and here you can see Sentinel-2, Sentinel-3, Sentinel-5. There's also Sentinel-1. And you import them, and you are ready to work with the satellite images. And I'm going to show you an example with how to visualize the Sentinel-2 images using Google Earth Engine. You should know that in the Sentinel-2, you have 12 bands. And on this graph, the bands are represented by the black line, the vertical line. So those are the bands of Sentinel-2. And I put here the full spectrum from the visible, 400 nanometer, to 2500 nanometer, passing by the visible. So that's what you can see, the blue color, the green, then the red, then the near infrared, and then the shortwave infrared. And the four colors here, in blue, this is the water content. And you can see that the reflectance that you can measure, if you want to measure the water, you have to start at 1100 nanometers. And then you have the peak where you can retrieve water. In the visible, you can retrieve information on the chlorophyll. That's the green pixel, the square there. And so using the channels in the blue, in the green, and the red of Sentinel-2, you can retrieve chlorophyll, as well as the internal structure, which is the orange dots there. So you can select, based on this graph, which information you want to retrieve and which bands you should use. For example, to retrieve water in the shortwave infrared at 1600, you can use one band, which is band 11 of Sentinel-2. And I'm going to show you a few combinations, but to display the images. But you can imagine that you can create any type of index by combining the bands to retrieve either the water or the chlorophyll or the dry matter here in green. And also you can see that if you use the band 11, which is at 1600 nanometer, that band is affected by the water, but the dry matter, and also the internal structure of the leaves. So if you want to retrieve water there, you need to use another band, which is affected by the internal structure and the dry matter in order to decrease the impact of those two values. And to do that, you can select any bands in the near infrared that are only affected by the internal structure and the dry matter. So if you want to retrieve water, you have to combine the information of the band 11 in Sentinel-2, in the shortwave infrared, with a near infrared there. So this is the type of combinations and creating methods to retrieve a particular component of the vegetation. And this is the example how you can display the satellite images that you receive. You can always use a combination of red color, green color, and blue color to represent any type of colors there. And the way you display the images is you select the band you want. For example, B4 is the red channel, B3 is the green channel, and B2 is the blue channel. So if you put the red channel to the red color, the green channel to the green color, and the blue channel to the blue, you have a true colors. So it's like what you see using your eye. But you can combine other bands like the middle infrared, the B11 in the red color, the B8, the near infrared in the green color, and the red channel in the blue. So that gives a false color, but where you can see features that are very prominent. You can see the vegetation in green, you can see the bare soil in pink or brown, and the blue will be represented for the water. And this is the example of the code that you can have access to the Sentinel-2 images. You select the date you want. Here it's August 2019, from the first day to the 31st. And then you select the bands. So here I select the band 4, which is the red, the green, B3, and the blue channel, B2. And I combine them in red, green, and blue composition. So I will have a true color. But I can select other bands, B11, the shortwave infrared, the B8, the near infrared, and then the red, the B4, and I will have different results. So for example, this is the result with my false color. And you can see the vegetation in green, the bare soil in brown. The blue there are clouds there, and the dark blue are the water. This is the true color there, and the true color, you have the clouds in white and in dark green, and with false color you have better contrast, for example, for the extracting the vegetation. And this is a technique that I use to extract vegetation in the desert. And in order to play now with the images, what I suggest, and I provide you the link, is to look at the Google tutorial on the language use. So you have examples of how to access the images, how you can create indices, how you can do statistic there. So I would suggest that you look at the tutorial, and that little by little you can build your own expertise and the way to extract particular information like the water, the vegetation, the clouds, and the bare soil. And you can open a lot of applications in agriculture, in forestry, even human diseases, and natural disaster. So I think I'm going to stop here for the presentation and open the floor for questions, and we'll try to answer.
Thank you, Pietro was right on time. So we have still time, few minutes for questions. So I think Cynthia will go with the first one.
So the question is, with this methodology, we can detect and characterization of edge rows with the optic images Sentinel-2, which is better level. I'm not sure what edge rows are. If you can maybe specify. Anyway, for any type of retrieving of vegetation or water, you can use either level 1C or level 2A. So level 1C, it's I think the correction, the atmospheric correction, and level 2A, it's the reflectance of the top of the canopy. So at the level of the ground level. So if you are not familiar with atmospheric corrections and other corrections that are produced to the satellite, it's better to use level 2A. Level 1C, then if you want to apply your own corrections, that's it's better to use level 1C. So I would suggest, yeah, if you're not familiar with all the corrections applied, to use level 2A. Yeah. Okay. Is there a time lag in Google Earth Engine? How long does it take for a recently acquired Sentinel images to appear in Google Earth Engine? There is a time lag, but it's almost the same that the one that you have to go into the Science Hub, which is the website where you can download the satellite images from Copernicus, from ESA. I'm not sure if it's an hour or 2 hours, but it's almost the same that the images that are available on the Science Hub from ESA, at least for the level 1C. For the level 2A, I'm not sure. It might have some delay there, but I've never checked how long it takes to do that. Next question, have you used any GNSS technology for in situ validation or inspection supported with Sentinel mapping? Any case study? No, I've never done that, but that's a good suggestion. And but personally, no, I've never done that. What we do usually, it's we go into the field, working with a research center that collect the data and do the measurements, and then we compare with the satellite images. And Google Engine can replace the DS. So the DS are the places where you can access the data, and you would be able to also upload your algorithm to work on the DS. There are several of them in Europe. Personally, I haven't tried to go to the dais yet. I'm still using Google Engine to do a little bit of research, but I have developed my own capacity here at Spacebell, where we have servers and we have processing chain to develop the product that we create. So yeah, Google Engine can replace the DIAS, and the DIAS can replace Google Earth Engine as well. It's a matter to connect and to find which one is easier of use. Yeah.
Okay, so it's time for the last question about machine learning, I think. Yes.
Okay, it looks like machine learning algorithm can help in the classification of images and objects. Do you know about application of machine learning in remote sensing? Yes. For the last 2 years now, I'm creating a line of research at the Spacebell to use machine learning. And the development goes so fast that it's even difficult to keep up. And so I'm working with universities where they have expertise in artificial intelligence, deep learning, and it's almost every month that you have new methods that are developed, and it's quite powerful. So I use more and more machine learning algorithm, convolution neural networks to do classifications and identifications of species, tree species or crops. And it's a new area of development of application, which is phenomenal there. Very good.
Okay, thanks a lot, Pietro. It was a very interesting presentation. And now we will leave the floor to Guillaume, our next speaker. So Guillaume, you can now activate your camera and your microphone. And yes.
Okay, does it work?
Yes. It works. We hear you. We see you perfectly. Thanks again, Pietro.
Okay, bye-bye.
Okay, good. So let's start with this presentation. Yes, okay. So hello, everybody. My name is Guillaume Rieux, and I work in Tyrannies, which is a small company based in Toulouse, in France. And in this company, we develop and commercialize services based on Earth observation data for different kind of applications. It can be agriculture or land monitoring or wine growing. So it was a pleasure to work in this MOOC. And in the first video, I presented one service developed in Tyrannies, so for water scheduling products to farmer. So this was the aim of the first video. In the second activity exercise, the aim was to use the EO browser to search, visualize, and process Sentinel-2 images to retrieve vegetation indices for crop monitoring, so to process data with online application. And now in this webinar, I would like to present to you some tools and services that can be useful to develop Earth observation service for resource management. And at the end of the presentation, I will come back very quickly on the irrigation scheduling service that is currently developed, because I think it's quite a good example of a concrete example of the kind of application that can be developed with Copernicus data. But let's start with a short introduction on how to develop Earth observation application. In Tyrannies, so we develop this kind of services, and I think there are three main things that can be gathered to develop this kind of services of application. First one is to have an access to data. So it can be Earth observation data coming from Copernicus program, but from other data providers, but also some other data sources. And we will see in the irrigation scheduling service that weather data can be very useful to create some added value, but also in situ data or validation data set and so on. So data is very important. tools and computing capacities are also very important. So you need to have algorithms, machine learning algorithms, as Pietro said, or storage and processing capacities, so using DIAS or using Google Earth Engine. Well, you need to have this kind of tools and computing capacities to manage all this data. And last but not least, and I think it is one of the most important thing, is to have an access to skills and resources. To develop one application, you need to have a very good idea of what are the end users' needs, what are the specifications of the service you want to develop, because you can do a lot of things playing with data and playing with all the computing capacities, but it's quite difficult at the end to answer one specific need and to have a useful application. So this was just an introduction, and in this presentation, I will spend a little bit of time on two things: the Copernicus data and different tools, software, and algorithms that can be useful to develop application. So the first one about Copernicus data, there are different platforms on which where you can find some well, the Sentinel products. There is the Sci-Hub platform, which is the platform developed by the ESA, by the European Space Agency, on which you can download Sentinel-1, Sentinel-2, and Sentinel-3 data. And we will see, well, if we have time, we'll see this platform later. And then you have different data. So this has been mentioned in the previous presentation. There are at the moment five data and information access services that are financed by the European Commission. And the aim of this platform is to offer companies or offer private space on which you can develop your algorithms, on which you can deploy your application. And the aim is to have your own algorithms just next to the data and to process all this data quite quickly. So these are the dias. If you have questions, we can discuss about it later. And then there are also some other open access platforms, such as the one we have in France. The name is PEPS, and we will see after what are the differences between the Sci-Hub platform. The other one is USGS, so it is the platform managed by the in United States. And then there are Amazon and Google Earth Engine that provide all this data and other services, as Pietro mentioned it in the previous presentation. So, well, there are different platforms, but something which is very important is to know the differences between all these platforms and all the data that can be downloaded from these different platforms. And this will depend both on the technical and business requirements of your own application. And the question you could have is, for example, what kind of data do I need? If I need Sentinel-1 images, Sentinel-2 images, do I need to process just one image once a year and of a small region of interest? In this case, maybe it's not useful to have a very complicated application. Or do I need to process a long time series of a large area and very quickly? And maybe in this case, Google Earth Engine application could be a good choice. Well, this is the kind of question you need to ask before starting to develop your application. And to be more concrete, I will present just two platforms, so the Sci-Hub platform and the French one, the PEPS platform, just to show you that there are some differences that can be important to take into account. So on this part, I will go fast. Just to the differences between the Sci-Hub platform and the PEPS platform. On the Sci-Hub platform, so the platform that is financed by the European Commission. You have all the Sentinel products anytime and anywhere. So you can have all the images you want, and you have both Sentinel. Well, in the case of Sentinel images, you have both Sentinel-2 L1C products, so which are the top of atmosphere products, and Sentinel-2 L2A products, but processed with a tool and algorithms, specific algorithms named Sentu-Core. We will see just after the differences, but it's quite important to see all these details. And for the PEPS platform in France, we can only download the bottom of atmosphere reflectance, so the level 2A images, on selected sites. So it's not available everywhere on the world, but they are processed with another algorithms, which is called Maya. And we will see just now, if I can share my screen. Yes, on this, we will see the differences between the reflectance value between L1C, L2A Sentu-Core products and L2A Maya products. And we will see also the differences between the cloud mask quality, which is a very important topic on Earth observation data, and then the impact on the Ndvi, which is a vegetation in this index based on satellite images. So we'll just share. Okay. Yes. Is it okay with the screen? Yes, the share screen. I guess so. Okay. Yes, it's fine. Okay, good. So these are three Sentinel-2 images that I have downloaded over Luxembourg. So this is the first one, the second one, and the third one. The first one, sorry, the first one. So this one is a level 1C image, Sentinel-2 image. There is no atmospherical correction, and as you can see, the colors are quite blue because there is no atmospherical correction. And when we perform atmospherical correction, the result is this one. So as you can see, there are quite a lot of differences between the reflectance values of the pixels between this one and this one. So it's quite important to correct all the effect of the atmosphere when you want to use optical images. And then there is also one difference between the algorithm you use to correct these effects. So this is the true color image of the Sentu-Core product, and this one is with Maya products. So as you can see, there are some small differences, particularly on the dark areas, but there are some differences. So it's important to have to think about this before starting to work with Sentinel images. And another thing which is quite important is the cloud masks. So with level 2A products, so the images with the correction, the atmospherical correction, there is one cloud mask. And in this case, this is for the Sentu-Core algorithms. So as you can see here, okay, no, sorry. No, there's, okay, I will not, okay. So as you can see here in blue, it's the different clouds. So the clouds and the shadows. So for example, if we go on this part, you can see that the algorithm can detect the clouds and the shadow, but there are some pixels that are classified as cloud, which are not clouds. So this is for the first product, and the same thing for the other algorithms which is called Maya, with the cloud mask. So as you can see, there are quite a lot of differences. In this case, we do not have some isolated pixels, but we have some pixels that are not cloudy, but they are in the mask. So depending your application, if you want to have very clean mask, you can use this one. If you want to have lots of pixels, even if sometimes there are some mistakes, maybe it's better to have to use Send2Core application. Okay, and then there was a last example with the Ndvi. So just to show you the differences between the atmospherical correction. So this is for the L1C Ndvi, so without atmospherical correction, and then this one is with atmospherical correction. So as you can see, there are lots of differences in the values, and this is important to take into account when you want to characterize, for example, the crop, the crop, if you want to describe the one forest and so on. Okay, so I will come back to the presentation. Good. And if you have questions, we can discuss about it later, of course. So this was just the same thing, but if the same thing. And then let's talk just a little bit about the tools and the computing capacities that are very important to manage when you want to develop the application. So there are mainly three kinds of tools. First are Gis Desktop Application. So there are mainly two kinds of softwares. One open source software called QGIS, and another one which is ArcGIS. So these are the two main desktop applications to handle satellite images, but also vector data and to create maps. Other softwares are image processing softwares. And for example, in this case, you have two commercial software, so Ndvi and Erdas, but there is another one which is NAP application, so which is the Sentinel application platform developed by the European Space Agency, and which is free, and you can use it to process Sentinel images and to process images and to run algorithms on these images. And then the last kind of tools are programming languages. And in this case, I just put two examples. The first one is Python, which is very useful to process satellite images. There are lots of libraries to do lots of things, including machine learning things. There are lots of libraries to use to process these images. And the other language is R language, which is also used to process Sentinel data, but also images. This, and if we have a little bit of time, I will finish the presentation with this example. So the irrigation scheduling product service developed by Tyrannies. So in this case, we use Sentinel-2 images that we download from the Sci platform. So the level 2A products. We compute Ndvi on these images, and the purpose is to monitor crop growth and estimate the crop evapotranspiration. So this is for the spatial data. Other data that are collected are weather data and in-situ data. So in this application, you need to enrich the algorithms with other data coming from weather data providers or from the farmers. And all these are used to estimate other indicators. So in this case, it is the soil water contents in the root zone of the crop. So all these are data are mixed to retrieve this indicator. So this is the conclusion. The conclusion, just to say that once again, it's very important to think about what kind of data are useful to develop the application, what are the existing tools and the computing capacities that are available to process everything, but also to have some good knowledge on the topic, on the topic of the application. Okay, good. So now, if you have some questions, I will try to answer them. So the first one, how difficult to measure crop yields in a specific area through Earth observation for amateurs? Sorry, there is, yes. In these highly specialized activities provided by companies such as your company, to estimate crop yields, it's quite difficult. It's quite difficult because it depends on lots of things, on weather data, on the soil type, and so it's quite difficult. There are some models that use Earth observation data and other kind of data to estimate the yields, but using only Earth observation data, it's not really well. It doesn't work very well. You can estimate other things, but not directly the crop yields. So, what called the difference in surface reflectance values between Situ and Maya? The differences is yes, can be explained by the approach of these two algorithms. First, on Situ, the Situ algorithm will use only one image to correct all these effects of the atmosphere, so on the water content of the atmosphere and so on. So it will use only one image. On the Maya algorithms, we will use several images, so a time series of image, to perform these corrections. So this can explain a part of these differences. And then it is, well, the algorithms are not exactly the same, so the reflectance values are a little bit different. What in situ data do you use for the application, GPS, Gnss, and what accuracy is expected for in situ measurements? So for in situ data, when I said in situ data is, for example, for the irrigation scheduling service, is the delimitation of the parcel and the crop type, the soil type, and this kind of information we need to have to develop the service. So they are not based on GPS or Gnss services. They are just knowledge that are gathered by the user. And what accuracy is expected? Well, we mainly use Sentinel-2 images, so the spatial accuracy is 10 meters for the pixel. So if you have, we do not need very precise precise location for this kind of application based on Sentinel images. What do you exactly for viticulture? Yes, for viticulture, in Tyrannies, we provide services to estimate the quality of the grapes for the wine. So we do not use Sentinel-2 images, but we use Spot 6 images, which has a better higher spatial resolution. So the resolution is 1.5 meters, and we extract from these images some biophysical parameters, some indicators to estimate the let's say the vigor of the vine, and then we work with actors on the field to estimate the quality of the wine that can be made with the grapes. Is it possible to monitorize vegetation development in small rooftop gardens or small community gardens? Well, using Sentinel-2 images, it's quite difficult because the pixel is 10 meters. So to monitor vegetation on small rooftops in cities, it will be quite difficult. So for this kind of application, it's better to use other images, other satellite images, such as spot images. So the resolution is, well, let's say 1.5 meters, or Pleiad images with the whose resolution is around 60 centimeters. So, yes. Thanks. Thank you, but it is still too difficult to access and use images for non-experts. Maybe this could be an application to simplify the process. Yes, to access and use images for non-experts. From my point of view, I think the easiest way to access images are Sentinel Hub application. So the EO browser developed by Sentinel Hub. So you only have to, well, you can access to these images with your internet web browser, and you can download, process these images. This is the first one, and after, if you want to have more other, other kind of application, the Earth Engine application can be a good solution. But first one is Sentinel EO browser developed by the Synergized company. Do you know SW, image processing library, Halcon and Vision Pro for satellite, for image processing? Is it possible to use it for satellite images? No, I do not know these libraries, so I cannot answer this question. Can you use Sentinel-2 for near real-time agricultural monitoring of crops in all developmental stages? Yes, but it depends on the crop type. I think for annual crops, it's quite easy to use Sentinel-2 images for crop monitoring. For perennial crops, such as vineyards or such as orchards, it's quite difficult to use this kind of data, this kind of images, Sentinel-2 images, because of the resolution and because the parcel is not very homogeneous. You will have rows, you will have sometimes grass between the different rows of trees or vines. So for annual crops, it's quite Sentinel-2 is quite good to monitor crops, but for other crops, it's a little bit different. Do you know if level 2A is the correct for detecting hedgerows? Yes, yes, I think it is the yes. This kind of product can be used to detect hedgerows. Yes, so level 2A is a good choice. Yes. Okay, another question. How do farmers in general react to Earth observation data application to their crops? It's a good question. In Europe, well, in France and with the partners we work in Europe, now they are used to work with this kind of data. at the beginning, all the satellite images were mainly used to control the farmers by the Common Agricultural Policy. The farmers were a little bit afraid by this kind of data, but now there are more and more services based on Sentinel-2 images, based on Earth observation data, so they can find the interests of these applications to help them in the day-to-day life, let's say. So now it's changing, and there is an interest in Europe. After in other part of the world, well, I cannot answer this question.
Thanks a lot, Guillaume. So that was the end of the second part of our webinar. And so now we will leave the floor for our last speaker, Diana, and we will start with a video. And after that, of course, she will be there with 3 guests to answer your question. So individually the
Hi,
sound.
my name is
the
Diana
video.
Chavarro Rincon. I work at the Faculty ITC of the University of Twente in the Netherlands. In this webinar, I want to show you some of our activities and how the Copernicus program has become a valuable instrument to fulfill our mission. First, I want to briefly introduce our faculty. Then I will show you some aspects of our work on capacity development. After that, and to illustrate how we are using Copernicus, 2 of our staff members will shortly present their work. To conclude, and after some final remarks, we all will be available for a Q&A session. The Faculty ITC of the University of Twente hasn't been always that, so let me tell you a bit of our history. ITC was founded in 1950 by a former Dutch Prime Minister as an independent institute with the name International Training Center for Aerial Survey, to provide training on cartography and geodesy and to support developing countries. With time, ITC evolved to become the International Institute for Geoinformation Science and Earth Observation in 2002, and in 2010 it became a faculty of the University of Twente. Over the years, the programs and mission of ITC have been adjusted to changing technology and societal challenges. Our fields of expertise include disaster management, food security, geohealth, governance, smart cities, and water management. ITC's mission is to empower society through capacity development, particularly in less developed countries. And we attempt to achieve that by working in these 3 different pillars: education, research, and institutional strengthening. ITC conducts education in a multicultural environment. Students from all over the world come to our faculty where they find an enjoyable atmosphere to carry out their studies. Research and education tasks are supported by fieldwork in the neighborhood of the faculty using adequate equipment, like for instance our 50-meter tower with instrumentation for energy fluxes measurements, or a network of soil moisture sensors installed in croplands. We also take our students outside campus for data collection, for example, on water quality in the northern coast of the country. Fieldwork also takes place abroad, like for instance in Kenya, as you can see in these pictures, China or Spain, just to mention some examples. We complement our face-to-face programs with distance online education. And of course, we have made the necessary adjustments to carry on during COVID-19, as you can see in these scenes, including converting a baby room in a working place for a working mother. Current challenges being faced by our students in their normal lives, such as drought, pollution, floods, etc., are tackled with the help of GIS and observations, for which we encourage the use of open source software and data, like, for instance, what is provided by Copernicus. Our in-house regular programs throughout the years, together with our joint education programs conducted around the world, have resulted in more than 20,000 alumni coming from 175 countries all over the world. We are also devoted to capacity development and institutional strengthening through international cooperation. For that, we follow reference frameworks such as the Sustainable Development Goals of the United Nations, the Paris Climate Agreement, or the guidelines of the Dutch government for international cooperation. Here you can see some examples of recent projects on capacity development in which Earth observations have played a fundamental role. For instance, initiatives funded by the European Space Agency, such as TIGER or EU4SD, or the NSAT project in Ethiopia, funded by the Dutch government, for which you will find here some details. I have with me Paria Pashasade. She works at our faculty, but she has been also involved in delivering training for our projects on capacity development. So tell us, Paria, in which context have you been involved in our projects?
First of all, thank you, Diana, for giving me the opportunity to be a part of this experience. When I was working as a lecturer, I had the chance to carry out several educational activities for capacity development in projects that focus on using Earth observation data for addressing global challenges. One of the most prominent ones was ESA's EU4SD Agri-Cluster initiative, where ITC was the capacity building partner. And during that project, we delivered more than 15 workshops and courses all over the world, in Africa, in Latin America, in Southeast Asia. So that was a fantastic experience.
Great. And tell me, in these projects, how important has been being able to use Copernicus data?
That's a great question. When it comes to capacity development, not only we have to focus on increasing knowledge and expertise in the institutions, but also to make sure that they have access to data and the infrastructure that is needed for them to be able to utilize the knowledge that they have obtained. And only by giving them the whole tool set of knowledge, expertise, data, and infrastructure, we can make sure that the real-world applications are going to benefit from it. In some countries, data collection and access to data is a major issue, sometimes due to environmental conditions, governmental regulations, or simply because the cultural complications avoid sharing data. So availability and accessibility of Copernicus data, combined with the trainings that we can deliver, enables many more people in these countries to address the common problems that they have. And therefore, it fosters growth and sustainable development.
Yes, but I'm sure that we still face some challenges to achieve our main goal, which is to facilitate the sustainable use of Earth observations, right? What can you tell us about it?
Indeed. So in the regions where internet connection is still a problem and the access to it or the speed of it is limited, we face serious problems in accessing the data and also in using cloud storage and cloud computing platforms. So the advantages of frequent and detailed data capture that is being done through Copernicus program, for instance, cannot be fully utilized. So we have to be more creative in finding a way to providing access to satellite-based data, product and services. As educators working in the field of geoinformation science, one of our main objectives is to show the potential and the added value of using satellite-based information. We usually start by teaching the principles of GIS and remote sensing, and we dive into more details according to the application domain. It could be urban planning, where we use maps and geoinformation science for planning and other decision-making purposes, or it could be different applications such as forestry and natural resources management. At ITC, we have the privilege of meeting students from all over the world, either in our regular educational programs or by visiting them for tailor-made trainings and refresher courses. Of course, we continuously work on increasing the quality of our distance education as well by employing innovative methods of learning. We hope that by creating awareness and understanding, we help the sustainable uptake of Earth observation in their daily practices and to support their ongoing projects and developments.
In the next section, Monica Kuffer and Mariana Bellew, both assistant professors of ITC, will show examples on the work on Earth observations for capacity development.
Hi, I'm Monika Kuffer from ITC University of Twente. I will talk about two projects, IdeaMap and SlumMap, both working on filling existing global data gaps on urban deprived communities using machine learning and Earth observation, and also responding to the present data needs in poor urban communities in the context of COVID-19. Looking to the context, it's estimated that around 90% of the global population increase will occur in low mid-income country cities. Most of this growth will happen in poor communities, as you see on the right side as an example, Kibera slum, and a community characterized by deprived living conditions, poor environmental conditions, and poorly serviced. What you can observe in existing official data sets is that data on such communities are often missing. Here shown for the example of Bangalore in India, where you see the blue dots are the poor communities which are not officially recorded in municipal data sets. In this situation of the city of Bangalore, many of these communities are temporary settlements which are highly dynamic across time. In the context of COVID-19 outbreak, using here the example of Salvador in Brazil, heavily hit by the present COVID-19 outbreak, we can observe that base data are missing in official data to support locally detailed strategies for COVID-19. Data which are presently missing are relating to environmental conditions, to the urban morphology, as well as to socioeconomic conditions. In the context of SlumMap projects, we are working on developing a free and open source framework that allows to provide information about the location and the extension of slums, as well as characterizing their physical environments. Very much focusing on developing methods which are limited in costs. A result shows for the city of Nairobi in Kenya, using Copernicus data, Sentinel-2 and Sentinel-1 images, shows a map which predict the probability of a grid cell of being deprived. But not only data at city scales are produced, but also data which characterize the physical environment of such communities. Here showing the example of the use of a very high resolution, but still free cost image of Google Earth in using machine learning, in particularly deep learning methods, to extract building footprints which allow to characterize morphological variation of communities such as building densities, distance between roofs, which are urgently needed in support of COVID-19 strategies. But also in contact with communities, we got the urgent information needs about monitoring the accumulation of trash piles, which have been occurring during the COVID-19 lockdown regime extremely in communities, and where we can use Earth observation methods for monitoring the accumulation of trash piles and showing their locations. Such data will be fed into a developing data ecosystem, which we are working on within IdeaMaps. They will allow to produce data in a gridded format to protect data privacy, which allow to produce data which showing the level of deprivation across cities, but also individual dimensions of deprivation, such as physical, environmental dimension, combined, for example, with population estimates, which are also urgently needed in support of COVID-19 strategies. To conclude, we need to produce data which responds to user need, and we need to develop user cases to show the potential of Earth observation. For this context, we are developing a platform of exchange and working in the co-creation process of knowledge, co-creation between Earth observation and local communities. We need to work on methods within the Earth observation community that are at scale, are scalable, produce data for purpose, but also producing transferable methods. Transferable meaning across cities, for example. To make data practically usable, we now have to deal appropriate with data ethics and data privacy. Data have to be locally accessible and need to be locally owned. Thanks for your attention. Goodbye.
Hi, I'm Mariana, and it's a great pleasure for me to talk with you today about the use of Copernicus data for my research. And I decided to share with you two activities which are interconnected and are related to crop types mapping and sensing hidden hunger using Copernicus data. We all know that the current population is increasing from 7 billion as we used to be in 2015 to more than 8 billion in about 10 years. And all this population growth will put a lot of pressure on the food security systems. Therefore, food security is high on the agenda of the Sustainable Development Goals, especially on the second Sustainable Development Goals, which is zero hunger. In order to address this goal, we need to develop operational crop types, mapping and monitoring solutions. In my work, in order to do that, I'm using Sentinel-2 multi-temporal satellite images and machine learning techniques. More specifically, I'm using random forest classifier, which is a classifier very popular in the remote sensing community. And the second classifier I'm using, or approach I'm using, is dynamic time warping. This is a bit new to the remote sensing community, but it's a very old approach. It was proposed in 1974 in speech recognition community, and these days we decided to use it because it proved that it can help us to align temporal sequences that might be shifted. And in agricultural applications, this can happen very often. Why? Because we have clouds, maybe because we have agricultural practices that might differ from one location to another location, and we also have weather conditions that might be different. In terms of the smallest unit of analysis I'm using in my research, I have to say that I'm not using only the pixels, but I'm using also the objects. So objects represent an aggregation of pixels that are generated through segmentation. And using these two approaches, I'm trying to classify crops in 3 study areas. In Romania, which is also my home country, in Italy and California. And in terms of the data set, as I already mentioned at the beginning, I'm using multi-temporal Sentinel-2 data. Using the two approaches I mentioned before, we managed to obtain accuracy ranging from, for example, 90% in the first study area to about 70 to 89% in the third study area. The differences among these areas consist in the diversity of the crops. So in the third study area, which is situated in the United States, in California, we have more crops cultivated in the same study area as compared to Romania, where the number of crops is limited, and therefore the investigated classifiers perform better. The second application domain I'm really pleasant to share with you refers to the hidden hunger. Maybe you know that hidden hunger refers to the micronutrient malnutrition. So this is a malnutrition that occurs when the quality of the food is not very good. In the past, a lot of studies focused on assessing whether we have enough food. So the quantity of the food was important, whereas the quality was basically ignored. Meanwhile, we realized that the quality is actually sometimes more important than the quantity. And what we are trying to do in this project called HiNutri, a project which is funded by the European Space Agency, is to use Sentinel-2 data and hyperspectral data to predict the abundance of micronutrients in the crop seeds. We are interested in predicting potassium, phosphorus, nitrogen, and iron, for example. And how do we do that? We have 3 main steps. We have the field campaign. Our study area is in the northern part of Italy. We have to collect the crop seeds. This is something that has already been done during this summer. The crop seeds have been sent to a lab, and the nutrients composition of those seeds has been investigated, so we know the abundance of all the macro and micronutrients we are interested in. And now, at this stage we are currently now, we are trying to develop machine learning models to predict exactly those micronutrients that we measured in the crop seeds. And the results of this work will be shared with the remote sensing community by the end of this year. All these research activities are really nice because they help us to solve societal challenges, but at the same time, the knowledge that we gain by using Copernicus data and by applying machine learning techniques is shared with the in-house students that we have here at ITC, but also with institutions, organizations, universities from developing countries. So one important pillar in our activity here at ITC is capacity building. Basically, we want, and we focus a lot actually, on developing tailor-made courses. These are courses that are tailored to the needs of the organizations, international organizations. And I want to give you an example of a NAFIC, tailor-made courses. This is NAFIC is the Dutch organization for internationalization in education. And within this project, we are using remote sensing data, including Copernicus data like Sentinel-2 and UAV, in order to show different organizations and agencies from Jordan how they can improve the quality of their food and water management. Thank you so much for listening to my presentation.
Well, this is what we wanted to tell you. In a nutshell, we use Earth observations to train our students to be able to convert the acquired knowledge into practical applications for solving real-world problems. Thanks for watching. Now, if you want to know more about us or our work, we are available for a Q&A session.
Thanks a lot, Diana, for this very nice presentation. So now we will start the Q&A session. And yes, so our guests are here.
Thanks. Can you hear me well?
Yes, we can hear you well.
Okay. Okay, so I have two of my colleagues online, and another one of my colleagues is sitting close to me. So we'll try to do the best we can do to answer your questions.
Okay, perfect. We start. Okay, we will start with a long one. So.
First to destroy, yeah. Hey, Monica.
Yes, sorry, can you hear me?
Yes.
Yes, good. To be honest, we have been just starting with this waste and trash pile monitoring, but very much in the focus of a situation of African cities, where we heard from local communities that is increasing a generation of illegal, or not illegal, but simply trash piles, which have been accumulating in the communities, is an emerging problem in the situation of COVID-19 lockdown. I know that illegal waste dumping is of course an issue, and we are now working with different types of sensor system, comparing the very high resolution sensors with sensors also from the Copernicus program, and to see how much we can get from this accumulation of illegal waste piles. What we see so far in the high resolution system, which is very much tailored to the very relatively tiny waste piles generated in the very congested slums, we get them relatively good with high-resolution systems. I would assume, particularly with larger illegal waste piles, you can, in principle, train them. And we are using CNN-based, so deep learning-based methods to train to detect illegal waste piles accumulation. I hope this answers your question.
Okay. Artificial needed to know whether Copernicus data is available to map urban heat island. Okay, maybe it's a question for you, Monica.
Sorry. Yes. Basically, I think so far we have been also doing work on urban heat islands. Very much. Also, most of our work we do outside Europe. So we have been working on detecting urban heat islands and also comparing the different socioeconomic categories of cities, particularly also to go into the poorer areas and see that particularly the deprived people living in deprived living conditions have an increasing exposure to high surface temperatures as compared to better off areas. And we have been then using basically thermal images from MODIS. So far, I have not been working with thermal images from the Copernicus program, very frank. So far, mainly using Landsat and MODIS images.
Okay, maybe we can go to the next one. Okay, maybe this is for Mariana. Oh, Mariana, unmute your mic.
To activate your mic.
Mariana, you are mute.
Right.
Just a second.
Mariana, do you hear
yes,
us?
I
Sure,
think
yeah.
Mariana is mute.
J'essaie de déverrouiller le micro.
Okay.
Mariana, you hear us? You need to unlock your mic on the video window because we cannot hear you. So just click on the video window and you will see normally two icons with the mic and the camera.
On your screen, yeah. Okay.
Now I managed.
Oh yes.
Okay. Yeah.
Okay, so you have to start again.
Yeah, sorry, yeah, please.
So monitoring agriculture with satellites, how do you handle farmland? So basically, we do have studies in developing countries like Ethiopia, where we have to deal with smallholder farms. And for this, when we map cropland, we can use Sentinel-2 data, and sometimes in combination with Sentinel-1 in order to address the problem of clouds. But if we want to map very small fields and also to map crop types, then we have to combine this with very high resolution satellite images in order to address this problem that you highlight here in your question. So basically, this kind of problem has to be addressed by using a very high resolution satellite images. Yeah.
Okay, now would micronutrient monitoring have used? Okay, this Mariana, do you think you could answer the question?
Yeah. So would the micronutrients monitoring have uses in relation to algal blooms in order to study the effects of pollution. Yeah, I don't have experience myself with this kind of application, yet I can imagine that hyperspectral images like those that are currently collected by Prisma, and in the future we will have also Copernicus, hopefully. So there are discussions on this. And so this kind of data can be indeed used for monitoring also algal blooms, as you mentioned here in your question. Yeah.
Okay. Okay, now you will get something.
Yeah. So I think I can take this as well. So
Yeah,
the question is whether the Sentinel images are sufficient to detect small cultivated areas. Well, the question is always how small the cultivated areas are. In the examples that we showed you with the 3 study areas in Romania, we have rather fragmented agricultural landscape. So some of the plots that we mapped there were pretty small, but again, so if they are extremely small, then the 10-meter resolution of Sentinel-2 might not be enough for this kind of application. Of course, you can go to sub-pixel kind of classification in order to solve this problem. Or, as I mentioned previously, you might want to use very high-resolution satellite images for this. Yeah.
Okay. The next. Okay, Mariana.
Yeah. The determination of the crop composition is made on how big surface. What is the minimum surface that can be considered? Do you take in consideration influence of other crop species nearby? That's a good question. We classify crop types. So, and as I said, we assess to what extent Sentinel-2 data are enough for identifying those particular crop types in that specific area. And we did not take into account the influence of the crop species that might be indeed nearby. Maybe something that is useful for others who are interested in this application. When we are applying machine learning techniques, when we generate the samples, we will always create a buffer around the agricultural field boundaries. So the size of the buffer, it depends, of course, on the size of the parcels. But if we have this buffer, we will ensure that the samples that we will use for training the machine learning classifiers are not incorporating the mixed pixels that you usually have along the boundaries, and which might be exactly influenced by this the presence of other crop species nearby. Maybe this might be useful for your work as well. But it's a great question. Yeah.
Okay. Spectral data also for Mariana. Yeah.
Yeah. So it's really nice, as I mentioned previously, that we will have several hyperspectral missions, and I do believe that some of the current limitations of the multispectral sensor when it comes to crop types mapping can be limited. But as I mentioned during my presentation, we are trying to investigate the potential of this sensor for other applications as well, like the macro micronutrients estimation. And this is extremely important, especially nowadays when we are dealing with a lot of food security challenges. But yeah, so the answer to your question is yes, and I do hope that we will see more applications on using hyperspectral data for crop type mapping. Yeah.
Yeah, and if I may add something to your answer, Mariana, I think the cost also is an issue in these cases. So when we want to provide a methodology for certain countries with limited resources or certain groups with limited resources, and we have to see which hyperspectral platform is available at low or free of cost.
Yeah. Yeah.
Okay. Please, what high resolution images can use?
So the images that we are always trying to use, as I said, we start with Sentinel-2 data. In the locations where we can find cloud-free images along the main phases of the vegetation growth of the crops we are interested in. So we try to use Sentinel-2, but as I said, if your smallholder farms are really small, then this is limited. And we know that these days is really difficult to find very high resolution satellite images that are available for free. There are different programs for research activities where you can get access to some to get data for free. This can be investigated for sure. Yeah.
Okay. Do we have time for another question? Okay.
And it's actually from Pietro, so our first speaker.
So what is your yeah, Piet, that's a very good question. We have just received in our project. We have partners from Italy, and they were responsible with pre-processing the data. And now we are at the stage when we develop the machine learning models, and now we have to assess to see the quality of the Prisma and the potential of the Prisma data for predicting the micronutrients. So at this stage, I cannot answer your question because we are in the processing stage in our project. But I'm happy to share with you on email our experience, of course. Yeah.
Okay, thanks a lot, everybody. So it was really a great webinar with a lot of questions. So yeah, thanks to all speakers and participants for this webinar. And we are looking forward to see you in the next webinar next week on Thursday, as usual.
Good.
So
thanks for inviting us.
Thank you.
Thanks a lot.
Thank you. Bye-bye.
Bye.
Thanks. Bye.